We are. Sorry about that, what I said. And we are going to share our screen and do an electrophoresis diagram. Some of you are tripping. You never talked about this in class. Not fair. Well, I talked about the principles behind it. Just remember, electrophoresis, you always have electrodes on each side. I want to remind you, this is the anode. You don't have to label it as an anode. Remember, anode attracts an anion, and a cathode attracts a cation because it has a minus charge. Cathode has this charge. So clearly indicate on each side which one's your plus and which one's your minus. I don't care if it's left to right, right to left, no big deal. You do need the PIs to figure out how far these objects move, these four objects. We have glue, sear, hiss, and a tripeptide glue, sear, hiss. And maybe earlier in the exam, we did the PI for glue, sear, hiss. So let's go find numbers we need. For glue, I need you to find me, there's only two numbers for glue, just give them to me off the handout. I need the pKa's for glue.
9.5.
9.5 plus, what's the other one?
4.1.
4 point, that's very high for a carboxylic acid. That's attached to an ammonium ion. Really? Are any of the CO2 minuses that high? Okay, I'm gonna trust you. 4 point what again?
4.1. I mean, there's another one that's 2.1, but if you're
This is, I have gly in my brain.
Oh, okay.
Yeah, glue we gotta think more about. Sorry. There's three numbers for glue.
Yeah.
And the 9.5 is irrelevant. Do you know how I know that? If you're looking at glue, it looks like this on the handout. Why? H3N plus CO2 minus CH2 CO2 minus. The first H that goes on goes here. So that will generate the PI molecule. So that number is clearly relevant. You've got to put it on. You got to get below the number you told me. 4.8 was it, or 4.9?
It's 4.07, so it's 4.1.
4.1. Okay, you told me that. I forgot. Now you got to get below that, but you can't go below this or else your molecule has a plus charge. If you go below this, it gets a proton. Stay above, what number is that? 2.1. And PI is, you add up, you get 6.2 over 2. This does not show the PI work here. Half of 6.2 is 3.1. Okay, I need that number. Serine, there's only two numbers for serine. This is the time I want you to just give me the two numbers.
9.2 and 2.2.
11.4 over 2 is 5.7, correct? 11.4 over 2?
Yeah, 11.4, yeah.
My numbers are there. So right now I know that glue is always more negative than sear.
Mm-hmm.
The lower the number, the more negative the species will be, because it'll have lost more protons than the other ones. Yes. It's like this one, except you're getting between the two nitrogens. You've got to keep the imidazole nitrogen off. I'm not going to show the molecule this time. The imidazole nitrogen was what, 6.1?
Mm-hmm.
This is for hiss. And the ammonium nitrogen is 9 point something?
9.2.
So that way you're gonna keep this one deprotonated and maintain this one protonated. Then one of your nitrogens is protonated. This is 15.3 over 2, and I'm just trying to help you with this. If it's odd at the end, make it 15.4, the next one up, divide by 2, and you'll have taken care of rounding on your own. So 15.4 over 2 is 7.7.
7.
I got that right, I think? It would be 7.65 if you just did the math. And then you'd round up to 7.7. Glue, sear, hiss. You actually have to draw that molecule to figure out what's up. But I suspect you did that already on this page somewhere. Glue, Sir, His, they're in order there. I'm going to draw glue, Sir, His. We're going to do it in red. Glue, carbonyl, CO2, like. And then we go, oh, perfect. We should have done blue, because blue is blue. I'll catch up with my color scheme now. Green is for Sir. NH is bonded to C that goes to CH2OH. I just got it off the handout, not on the page. I just happen to know that one. I got it right though, I hope. And then we're going to go purple. NH goes to a C that goes to His. CH2 goes to a ring. My memory's not what it used to be on. Yeah. Can somebody verify that's the right way to draw the His? Where it attaches is a double bond to C that goes to an NH. Did I get that right?
It's a double bond
Double
that
bond
goes
C
to an
immediately,
NH,
and then an NH,
and then
two double N, and then back to the where it's attached. Okay, and we
Yeah.
need a CO2 minus there. And right now you're looking at a molecule with a -1 charge, right? Just the way you drew it from the handout. So we got to get rid of one of the minuses. Which minus? The better base. Which is the better base? The 4.1. When it was an acid, it was 4.1. The conjugate base is pKb is close to 10. This CO2 minus, the number was, I didn't even write it down, but it's from His. The carboxyl of His is around 2. That's all you need to know. And that means the base here is 12. 14 minus 2 is 12. 14 minus 4 is 10. 10 is a much better base than 12. So I do need this number. What is the number for His's carboxyl?
1.8.
1.8.
It's 1.77. So if you
Okay,
round
1.8 was rounding. Okay. Because I have to take this put this H on, so get below 4.1 to do that, and keep this H off. Stay above 1.8 to do that. The PI for this is 4.1 plus 1.8 over 2. It's going to be 5.9. Remember, in your brain, just make that 6.0. And divide by 2, get 3. There's your answer with rounding. Sadly, I use black again. Doesn't matter. Okay. I'm thinking elsewhere on this very exam, and I'm going to try my best to make sure all this pre-work was from previous questions anyway, so you didn't have to do it again. Because we haven't even started answering this question except for this drawing we started. So I got 1 out of 5. I need to pick a value for a buffer. There's a buffer. It doesn't say. Diagram the electrophoresis experiment for separation of the following species at pH equals X. How do you get pH X? You dissolve everything in a buffer. And I want the best separation between everything. So if you choose 7.7 as your buffer, everything is going to be, let's see, 7.7 is above all the PIs except 1. Everything's going to be deprotonated, moving this way. There'll be nothing on the right side of the page. Nothing to the right of half. You could have wasted half your chamber. I need a median number. I don't even need it to be mathematically exactly median. Something in the middle of the two extremes, 3 and 7.7. Why don't you make your life easy? I need the middle of 3 and 8. Isn't 7.7 close to 8? What's the middle of 3 and 8? Well, it's half of 11. It's 5.5. Let's make the middle 5.5. Want to make the middle 6? Just to make it easier? I'm going to choose the middle to be 6. Something reasonable. It spreads these things around. I'm going to choose a value of x of 6.0. There's no right answer for x. So that means that serine is going to be close to the pi molecule, but a little deprotonated. 6 is above 5.7. So serine is going to lose some of its protons, not a great fraction, and become slightly negative. So if the middle is right here, I'm just going to put an imaginary middle in unobtrusive gray. And eyeballing the middle of the page is right there. Just remember, that's my 6.0. If something had a pi of 6.0, it would be right on this line. It wouldn't move. Okay? But 5.7 is a little deprotonated, which means it becomes an anion a little bit, and it moves towards the plus a little bit. Tell me you know this by doing it this way. I'm going to do all of my strips in baby blue. Real close to 6.0. And that represents SEER. S-E-R. I put that in there. That strip is where you would find this in the chamber. And the experiment's kind of cool. You would hover a UV light over it, and you'd see that glowing strip, and you'd actually cut it out with a knife. And then rinse the polyacrylamide gel with solvent to get your serine by itself pure. Yes, electrophoresis is for purifying these four things away from each other. All right, 7.7 is quite a bit higher, so it would be more to the left. This difference was only 0.3, and this difference is 1.7 between 7.7 and 6. So 1.7 and 3 is like 1.8 and 3. 8 times bigger. I need 8 times bigger gap between here and here. I need 8 times that to get to here, about here. 1, 2, 3. I'm just using my fingers here. 4, 5, 6, 7, 8. It moved a lot. It's way over here now. And here it is. What's the 7.7? It's my His. A little too tall. The H. That's going to be in that strip. What about the ones on the other side of 6.0? 6.0 is going to deprotonate these. Oh, they're all deprotonated. Wait a minute. 6 was below 7. Oh my goodness, Dr. Whitaker, what are you doing? I almost made this video worthy of erasing. Let's talk about the huge mistake I made. And go back to first principles. 6, the environment is below 7.7, correct? When the environment is below, that means it's more acidic than the 7.7. The environment will protonate the 7.7. Put an extra proton on it. Put an extra proton on it. Your charge doesn't become minus when you put a proton on something, it becomes plus. How plus? Well, a difference of 1.7 is it's going to be almost fully plus. I had this on the wrong side, is what I'm trying to say. Way over there. Yeah, this difference was 0.3 in the other direction, where 6 was above 5.7, right? So I'm going to make it clear, I hope. The difference of 0.3 between 6 and 5.7 moved this a little bit to the left because 6 is basic compared to 5.7. Serine lost some of its protons and became minus, which attracted it towards the plus electrode. Start over. 6 is below 7.7. 6 is more acidic than 7.7. 6 will protonate 7.7. When you protonate something, you make it positive. It attracts towards the minus electrode. How much? 8 times more than this attraction towards the positive. Why 8? Because the difference here was 0.3, and the difference here is like almost 1.8. Multiply 0.3 times 6, you get 1.8. It's like 6 times more attracted. So the gap here is 1/6 of the gap here. Going the other way, we're going back to everything below here. 3.1 is how far away from 6? It's about 2.9, right? Let's call it 3. And this gap represents 1.8. I can't have it that far over. I'm not going to be using a ruler and measuring. All I'm saying is this one, this 3.1 has to move a lot more than the 7.7 did in the other direction, because the gap's different, a lot higher. This one's going to go almost to the end here, and the 3.0 is going to go even further. So we need 2 more squiggles. No, you don't do that. Got to get this question done. So we're over an hour already. Copy paste. The one that's real close will be the 3.0. And right beside it, but still separated from it, be the 3.1. And the 3.1 was blue. G, L, U. And the 3.0 was blue, stir, hiss. Glue, stir, hiss. There's all your points. And that's the experiment you would actually see in front of your eyes. You'd use a knife to cut these 4 things out. You'd have them pure after you rinse them off the acrylamide gel, which is the medium for the separation. Okay, and just one last comment. You'll learn when you do the biochemistry, it's not just about charge. It's also about size, and that's a factor. The bigger molecules have a little more trouble traveling through the polyacrylamide gel. It has little pores that hold things up a little more, but we're only focusing on charge in this course. So I got myself covered there, so my biochemistry friends don't give me a hard time. And I think you get full credit for this, and we're going to stop. Coming back with one more, I think.